parallel plates. Okay? Please put down the heading. Viscous flow between parallel plates. This is also known as Coutte Flow. Coutte. Named after scientist Coutte Flow. Coutte. Coutte Flow. Okay? Yes, sir. So for this we are considering two parallel plates which are fixed parallel plates. This is the velocity, free stream velocity before entering to this gap, before entering inside this gap, and this is the exit condition. Okay? The distance between these two parallel plates, we are assuming it is small t. Small t is the gap between these two plates. Okay? Now I am considering a small rectangular element, okay, inside this plate at y distance. At y distance from this fixed surface. So the width of this element is dy and the length is dx. Dx is the length, dy is the width, and the depth we are assuming it is unity. The depth of the element is unity. So the area will be dx multiplied by 1 of this face, and area of this face will be dy multiplied by 1. Now the forces acting on this element will be the pressure force. So pressure force acting in this direction will be P into dy into 1. Pressure into area. And from this direction the pressure is P plus into dx and dy multiplied by 1 area. Clear? Now the shear force will be on this plane. So shear force on this and shear force on this surface. So shear force on this, shear force will act like this. On this rectangular element, shear force will be act like this. So the value will be tau into, suppose tau shear stress multiplied by area. So tau into dx into 1. This will be the shear force, and in this direction shear force will be tau plus d tau by dx dy. Sorry, in y direction. Shear stress changes in y direction. Del tau by del y into dy dx multiplied by 1. Now again we are assuming that the flow is uniform and steady. So for uniform and steady flow, acceleration will be 0. Flow is uniform and steady. That's why the total acceleration will be 0. Similar to previous case. Now the forces, the net force on this element will be P into dy minus P plus del P over del x into dx into dy minus tau into dx plus tau plus del tau by del y dy into dx and equal to 0. This is the net force. Okay? Clear? Now this p dy to p dy gets cancelled out. Tau dx to tau dx gets cancelled out. Now the remaining equation is minus del p by del x into dx into dy plus delta of by del y dy into dx is equal to 0. Is it clear to you? Now what we get? Del p by del x is equal to minus delta by del y, or minus sign gets cancelled out. Del x is equal to delta by del y. This is the relation. Okay? Just put it equation number 1 as equation number 1. Now I want to calculate the velocity distribution. So to calculate velocity distribution from the Newton's law of viscosity, we know tau is equal to mu du over dy. So tau is equal to mu du over dy. Just substitute the value of tau in this equation number 1. So we get del p by del x is equal to mu del 2u over del y. Del 2u over del y. Further, this one can also be written as del 2u over del y square is equal to 1 by mu del p by del x. Clear? Now integrate it. Yes. After integration, we get del u over del y. Del 2u over del y square becomes del u over del y is equal to 1 by mu del p by del x into y plus c1. Integrating with respect to y, there's del u over del y is equal to 1 by mu dt by del x into y plus c1. Now again integrate it. So integration second time with respect to y, it will become u is equal to 1 by mu del p by del x y square by 2 plus c1y plus c2. So we have two constants of integration, and the constants of integration can be determined with the help of boundary conditions. So now we will substitute the boundary conditions in this equation to get the values of c1 and c2. So boundary conditions will be, now if the y is equal to 0, means y is equal to 0 is this solid surface. So what will be the velocity at solid surface? 0. No slip condition. So 0 velocity at y is equal to 0. So y is equal to 0, u is equal to 0, and if y is equal to t, y is equal to t means the upper solid surface. At upper solid surface again velocity will 0 because it is a fixed surface. Velocity with respect to this plate will be 0. If the plate is moving, then also relative velocity will be 0 because no slip condition will also be again. Clear? So at y is equal to t, again velocity is equal to 0. Now substitute those boundary conditions. So when we put y is equal to 0, u equal to 0, this term becomes 0, y equals 0, this y becomes 0, so c2 will be 0. With the help of this boundary condition, c2 will be 0. Now the value of, put the value y equals to t and u equal to 0, we get 1 by 2 mu del p by del x t square by 2 plus c1t. C1t. So we get c1 is equal to minus 1 by 2 mu del p by del x into t. t. This is the value of C1. Clear?
Yes, sir.
Minus 1 by 2 mu del P by del X into t. Just substitute the values of C1 and C2 in this main equation. So we get velocity is equals to 1 by 2 mu del P by del X y square minus 1 by 2 mu del P by del X into t into y. Clear?
Yes, sir.
Now I am taking this term as common. 1 by 2 mu del P by del X, 1 by 2 mu del P by del X as common. Okay? What we get? U is equal to, I am taking minus sign also outside this bracket, minus 1 by 2 mu del P by del X ty minus y square, because minus sign I have taken out from this bracket. So ty minus y square. This is the velocity equation or velocity distribution. As you can see, the u is depends upon the square of y. It is an again equation of parabola. So distribution of velocity will be parabolic in nature. So parabolic distribution. So if you draw the velocity distribution, just substitute the value of y is equal to 0. So y is equal to 0 means either this surface or this surface. Either this surface or this surface. Y is equal to 0. Or you can say y equal to t. So if y is equal to 0, then the velocity will be 0. If y is equal to t, again velocity is equal to 0. Means the velocity at the surface of those plates will be 0. And substitute y is equal to t by 2. Now, at y is equal to 0, velocity is equal to 0. At y is equal to t, again velocity is equal to 0. These are the boundary conditions of our assumption. So, if those velocities are 0 at the surfaces, just substitute the value y is equal to t by 2. So, u will be u max. U will be u max at y is equal to t by 2. So, I am drawing the velocity distribution. This is the t by 2. At t by 2 velocity is maximum, and at surfaces velocity is 0, and it is parabolic in nature. So the distribution curve will be like this. Maximum at center and 0 at surfaces. This is the velocity distribution. U is equal to u max and u is equal to 0 and u is equal to 0. This is the velocity distribution when the viscous flow between parallel plates. So everybody understood it?
Yes.
Any doubts? So maximum velocity will be at t by 2. What is the value of maximum velocity? Substitute the y is equal to t by 2. So we get u is equal to minus 1 by 2 mu del p by del x t into t by 2 minus t square by 4. U is equal to minus 1 by 4 mu del P by del X T square. 8 mu minus 1 by 8 mu del P by del X into T square. This is the value of U max. The maximum velocity will be minus 1 by 8 mu del P by del X T square. Okay? So, after this maximum velocity, we need to calculate the average velocity. Okay? So, average velocity. So, next will be the average velocity. So what we will do to calculate the average velocity? What we will calculate first? The discharge equation. So I am considering the discharge through this element. Discharge through this area. dy into 1. I am considering from this small area the value of discharge, then integrated to calculate the complete discharge. This must be equal to the total discharge, means the area into velocity, average velocity. Okay? So first I am calculating the discharge through this small area, that is dq, means the area of element multiplied by the velocity at y. Velocity at y. So area of element is dy multiplied by 1 multiplied by the velocity is, this is the velocity, minus 1 by 2 mu del P by del X Ty minus y square. To calculate the whole discharge, we need to integrate it from 0 to t. So integration from 0 to t. So integration from 0 to t, we get the total discharge Q. This will become the total discharge. Q is equal to, this term comes out from the integration, minus 1 by 2 mu del P by del X, and the integration will be T y square by 2 minus y cube by 3 and 0 to t. Put the limits in this integration, we get minus 1 by 2 mu del P by del X t cube by 2 minus t cube by 3. Q will be minus 1 by, after the solving it, we will get 6 will be the LCM of this.
Yes, sir.
So it will become minus 1 by 12 mu del P by del X t cube. 3t cube minus 2t cube, single t cube is remain, so t cube. This is the discharge, minus 1 by 12 mu del P by del X into t cube. This is the value of discharge. Okay? And the velocity has minus sign in this. So from previous, you know, the minus sign indicates that the del P by del X must be negative. Pressure must decrease in the direction of flow, because velocity is positive. For the positive velocity, the sign of del P by del X must be negative. Similarly, okay? So we have calculated discharge here. Now what will be the discharge on the average velocity basis? So on the average velocity basis, discharge will be Q into area multiplied by U bar. That is average velocity. del P over del X into T cube, and area is T into 1. The total area will be T multiplied by the depth is 1. So T multiplied by 1. This is the total area multiplied by average velocity U bar. So T to T gets cancelled out, remaining is T square. The U bar will be minus 1 by 12 mu del P by del X into T square. This is the value of average velocity for the case of flow, viscous flow between parallel plates. This is the value of average velocity. Clear?
Yes.
Has everybody understood it?
Yes, sir.
Any more doubts?
No, sir.
Thank you. So we will move further. The ratio. Now we will calculate the ratio. The ratio will be the ratio of maximum velocity to the average velocity. Ratio of max velocity to average velocity. So U max divided by U bar. So U max from this and U bar from here. Just divide those, so you get 3 by 2. So for the viscous flow between parallel plates, the ratio of maximum velocity to the average velocity is equal to 3 by 2. And the flow, when the viscous flow through circular pipe, then this ratio is equal to 2. Okay? So in examination, please remember this thing. Then which type of flow is there? If the flow is through circular pipe and viscous flow is there, then this ratio is 2. And when the viscous flow between parallel plates, this ratio is 3 by 2. Understood?
Yes.
Now the pressure drop. Pressure drop. So drop of pressure. Drop of pressure. So to calculate the drop of pressure, suppose this is the x1 point, this is x2. From this reference, this distance is x1, this distance is x2. So x2 minus x1 is L. x2 minus x1 is equal to L. Now we have the average velocity is this. It is the average velocity. U bar is equal to minus 1 by 12 mu del P by del X into T square. Del P is equal to minus 12 mu U bar upon T square into del X. Integrated from 1 to 2, minus sign I am taking this side, 1 to 2, del P is equal to 1 to 2, 12 mu U bar divided by T square del X. After integration we get P2 minus P1 with minus sign is equal to 12 mu U bar divided by T square multiplied by x2 minus x1. So this will become P1 minus P2 is equal to 12 mu u bar into L. X2 minus X1 is L divided by T square. Just divide this equation by rho g. So it will become P1 minus P2 divided by rho g. Rho g. This is the loss of pressure head. Can be termed as HF. Loss of pressure head is equals to 12 mu u bar L divided by rho g T square. Rho g T square. This is the loss of pressure head, and the flow is between the parallel plates, and it is a viscous flow. Now one thing we forget to calculate, that is the shear stress distribution. So shear stress distribution. Shear stress distribution. So shear stress distribution will be, we know that tau is equals to mu d over dy. Tau is equals to mu d over dy. Substitute the value of u here. Substitute the value of u. What we have calculated is the value of u? Minus 1 by 2 mu or 4 mu? 1 by 2 mu del p by del x py minus y square. So integrate, just differentiate it.
Yes, sir.
With respect to y, tau will be mu multiplied by minus 1 by 2 mu into del p by del x, and differentiation of will become t minus 2y. So mu to mu gets cancelled out. Tau is equals to minus 1 by 2 del p by del x t minus 2y. Okay, this is the shear stress at y. This is the value of shear stress at y. Now shear stress distribution, as you can see, is proportional to y. It is the proportional to the value of y. So linear in nature. Linear. The nature of this distribution will be linear. So if you draw, this again, the shear stress distribution will be linear in nature. Put T is equals to T by 2. Put T is equal to T by 2. So at T by 2, shear stress will be 0. At T, this will become T, y is equals to T by 2, 2 gets cancelled out, T minus T is equals to 0. Surface, that is, it is very clear with the general understanding. The more resistance will be at surface, maximum resistance at surface and minimum at the center. That's why the shear stress is 0 at the center, and the shear stress is maximum at the surface. So this will be the shear stress distribution at T by 2. Tau is equals to 0, and at this point tau is equals to tau max. Again this point tau is equals to tau max. This is the shear stress distribution for Coutte flow. For Coutte flow. Clear to you?
Yes,
so Coutte flow is clear to you?
Yes,
the average velocity is 3/2. Okay, the velocity distribution is parabolic in nature. At center, velocity is maximum, and the plate surface velocity is 0. For shear stress distribution, at center shear stress is 0, but at surfaces shear stress is maximum. Clear to you? This will be all in the Coutte flow. Thank you.